Okay, in this video, we're going to go through intermolecular forces. So let's first take that word apart, intermolecular. It's kind of a big word, so I think it's always a good idea to break it down. So inter means like between, and then molecular means like a molecule. So intermolecular forces, it's talking about the forces between molecules. So we'll define it a little further and say that intermolecular forces are the forces that attract neighboring molecules. Okay, so there are three main types of intermolecular forces. The first is London dispersion forces, and I'm going to use the abbreviation LDF to stand for London dispersion forces, just because we talk about them all the time and I get tired of writing out London dispersion forces. We also have dipole-dipole forces. I use the abbreviation DD. Then we have hydrogen bonding, which I use the abbreviation HB. Now, I arranged these in this way because I wanted to show how London dispersion forces are the weakest of intermolecular forces, and hydrogen bonding is the strongest of intermolecular forces, meaning that dipole-dipole forces are kind of in between. They're not super weak, they're not super strong, they're in between. What's interesting is that when we get a whole bunch of London dispersion forces together, they can be strong. But what I'm saying is that individually, if we look at a little bit of London dispersion forces or a little bit of hydrogen bonding, the hydrogen bonding is much stronger than the London dispersion forces. And intermolecular forces are so interesting because they have so many huge effects, both physically and chemically. So one of them is like viscosity. So you can think of that as like the thickness almost of a liquid. So like molasses, for example, is a really thick feeling liquid, whereas like ethanol is a really not thick feeling liquid. So it's by understanding intermolecular forces and using them, that scientists have been able to create a new possible glue for surgery, which was inspired by slug mucus, which I think is simultaneously horrifying and awesome. If you are into doing crafts or anything, I like doing crafts. I'm not very artistic. I try, but yeah, most of my creations never see the light of day. But one thing among crafters that use glitter is that glitter sticks to everything. You use a little bit of glitter and you're going to be pooping it out for the next few days. Not really, but it gets everywhere. And so why glitter sticks to everything? That has to do with intermolecular forces. So let's get to what these intermolecular forces are. And we're going to start with the weakest type. So we have London dispersion forces. And London dispersion forces say that as molecules, whatever they are, as they get close together, their electrons repel. And honestly, it's more complex than this. See me for an explanation. I might link it in an extra video, but we can understand it by thinking of it this way. So as molecules get close together, their electrons repel, and an instantaneous dipole is created. So, and an instantaneous dipole is created. So hold on a second. What does dipole mean? Well, we saw that previously when we saw a separation of charge. So there was an atom that had a partial positive and an atom that had a partial negative. And that's exactly the same thing here. So dipole means like two, and then, so di means two, and pole is you have two poles of a magnet. So it's like that. So an instantaneous dipole is created, and they're momentarily attracted. However, this is not very strong, so it goes away quickly. So not very strong, so it goes away quickly. So you can think of it like this. If we have this molecule approaching this molecule, they both have their clouds of electrons. And as this molecule's electrons are circulating around it, there's going to be a time where, maybe there's a little bit more electron density over here. So overall, just for a second, not even a second, but a split second, there's going to be more electrons over here that have a partial negative charge. So the electrons over here on this molecule, having kind of congregated over to this side, they're going to repel the electrons from this molecule. And so these electrons are going to maybe kind of move over to the other side, which is when they leave, or when they move slightly over to the other side, that is going to create a partial positive charge on just part of this molecule. Now, these partial charges can then attract each other. So I am drawing this attraction as a dotted line, and this again is London dispersion forces are exhibited by all molecules because all molecules have electrons, and electrons are constantly moving, right? They're clouds of electron density. So this London dispersion force is something that is instantaneous, so it just happens, snap like a snap. And it's weak, and it doesn't last because the electrons are going to continue to circulate. So it's instantaneous, it's weak, and it doesn't last. So while the electrons are, over here for a split second, and that makes these electrons, move away over here, which creates a partial positive charge over here. In the next split second, these electrons that are over here may be going to, move away over to the other side of the molecule. And so this isn't something that's permanent because there's not a permanent dipole. There's an instantaneous dipole. Okay. So speaking of dipoles, let's go to the next type of intermolecular force, and that is dipole-dipole forces. So dipole-dipole forces occur when we have two molecules that both are polar. So we have only polar molecules. So what is a dipole-dipole force? Well, as these polar molecules get close together, their permanent dipoles attract. So again, the permanent dipoles, that's referring to the permanent separation of charge. So this attracts, and this attraction is pretty strong, and it's permanent, right? Because like the atoms are fixed, and where the electrons are, if one is more electronegative, it's going to pull it towards itself. Okay, so strong and permanent. So let's look at an example of what this actually looks like. And for this, I need to put in these electrons because I missed those. So we decided previously that this was an example of a polar molecule, right? Formaldehyde is polar. We can see that because it has one and only one polar bond. So overall, the electrons are congregating more toward the oxygen than they are toward anything else, and the distribution of charge is uneven. So I'm going to draw this in terms of partial charges. So we have a partial negative charge on the oxygen and a partial positive charge on the carbon. So then same over here, partial positive on the carbon, partial negative on the oxygen. Again, remember the partial negative is on the oxygen because the oxygen is more electronegative, so it's better at attracting electrons towards itself. Okay. So these two molecules, when they see each other, obviously they don't actually see each other, but when they interact with each other, there's a strong partial positive on one that can arrange itself to be right close to a strong partial negative on the other. Okay, so I'm going to draw this little dotted line to represent that strong attraction. So this is an attraction that's permanent, that's strong, and that lasts. Okay, so permanent, strong, and lasts. And again, it's permanent because these electrons are permanently more congregated around the oxygen than they are around the carbon. So that's what I mean when I say that it's permanent. Okay, so we can tell if something has dipole-dipole forces if we're looking at two molecules that are polar. And then just as review, we can tell if something has London dispersion forces by seeing, okay, is it a molecule? Is it a thing? Does it have electrons? And if the answer to that is yes, then yes, it has London dispersion forces. So what about hydrogen bonding? Well, hydrogen bonding is actually just a really special and specific type of dipole-dipole forces. So you can think of it as an extreme case of dipole-dipole forces. So extreme case of dipole-dipole forces. And another thing that I want to note here is that, before we actually get into defining it, is that the term hydrogen bonding, it's kind of misleading. We can get useful information out of it in that it has something to do with hydrogen, but when it says bonding, usually we think of that as like an actual sharing of electrons, and this, by definition, being an intermolecular force, there isn't really an actual sharing of electrons. So it's not a bond in the way that we think of a bond. I don't like the name hydrogen bonding. But what is it and how does it happen? Well, as molecules get close together, if we have really, really, really strong permanent dipoles that attract each other, then that is hydrogen bonding. And I'm going to write this out again. So it's permanent and really, really strong. Then that is hydrogen bonding. So for something to have these really, really strong permanent dipoles, we have to have some specific criterion that are met. And so that criterion, first off, is that you have to have a hydrogen, right? Hence hydrogen bonding. And that hydrogen has to be connected on one molecule to an oxygen, a nitrogen, or a fluorine. So that's the first part, that we have to have a molecule. So let's write that out, that we can have a molecule that has an NH bond, an OH bond, or an FH bond. Then this molecule that has an OH, an NH, or an FH is going to be interacting with another molecule that has, another molecule, I sometimes forget the U in molecule, with another molecule that has an O, an N, or an F. So notice that with this, only one of the molecules has to have an H connected to an O, an N, or an F. The other molecule, all that it has to have is an O, an N, or an F. And I'll give you an example of that in just a minute. First off, I want to go through a typical example of hydrogen bonding where we have that both of the molecules are the same and both of those molecules are water. Okay, so we decided that water is definitely a very polar molecule, and there's going to be a strong partial positive charge on the hydrogens and a strong partial negative on the oxygens. So partial positives on the hydrogens and partial negatives on the oxygens. So when the partial positive on the hydrogen in one molecule sees the strong partial negative on the oxygen of the other molecule, they are going to be very, very attracted to each other. And again, this is something that's really, really strong, and it's permanent, and it's something that lasts. So before we get into applying this, I do want to be explicit about the term, the terms that we need for hydrogen bonding. So let's look at, for example, if we have a water molecule and let's say a formaldehyde molecule. Okay, so we're doing this and we're trying to figure out the intermolecular forces between between these two molecules. And yes, intermolecular forces, they don't have to be between the same type of molecule. They can be between two different types of molecules. So the first thing that we're going to do is ask, okay, are there going to be London dispersion forces? Well, these both are molecules. They have electrons. So yes, there will be London dispersion forces. Okay, so yes on London dispersion forces. Next, we're going to ask, are they both polar? Well, water is polar, we decided that, and formaldehyde is also polar, we decided that. If we weren't sure about that, we could go back and draw in the bond dipoles. So identify the polar bonds, think about the shape, and then figure out if the molecule is polar or nonpolar. Since these are both polar molecules, they will have dipole forces between them. So the last one that I think is in many ways the most challenging is determining if it has hydrogen bonding. But I think in some ways it's the least challenging, like at the same time it's a weird paradox, because as long as you know this definition, like you can find it super easily. So it's just remembering, okay, you have to have one molecule that has an H directly connected to an N, an O, or an F. So here, okay, well in the formaldehyde we have an H, but that's not directly connected to an N, an O, or an F. So the formaldehyde isn't going to work for that part. But the water, we have a hydrogen that's directly connected to an oxygen, so that'll work. That takes care of that first part. Okay, so then we look at the rest of the definition and say, okay, we have a molecule that has an OH, so the H is directly connected to the O, and it's interacting with another molecule, and this other molecule only has to have an O, an N, or an F. It doesn't have to have a hydrogen directly connected to it. Okay, because this is going to have a strong dipole even if it's not directly connected to a hydrogen. Okay, so since this has an oxygen, then even though it doesn't have a hydrogen connected to the oxygen, this one, the water, provides the hydrogen that's connected to the oxygen. So this will indeed have, these two molecules will indeed have, we already decided they had London dispersion forces. They will indeed have hydrogen bonding between them. And this is the process that we need to go through whenever we're trying to figure out the intermolecular forces between two molecules, whether they're two of the same molecules like water and water, or if they're two different molecules like water and formaldehyde. So let's go ahead and do some practice with that. Okay, go ahead, pause the video, try it out. We'll go through it together in 3, 2, 1. Okay, so the first one is London dispersion forces, as always, and dipole forces. Because both of these molecules are polar, that means that they'll have dipole forces between them. So they do not have hydrogen bonding. And I bet that some of you were tricked by that. And that's why we do practice, right? It's so that we can catch mistakes and learn from them. So you might have seen, okay, well, there's a hydrogen and there's an oxygen, and thought, okay, that's enough. But remember that for hydrogen bonding to occur, on one of the molecules, the hydrogen it absolutely has to be directly connected, like as in sharing electrons with an oxygen, a nitrogen, or a fluorine. We have hydrogens in here and we have oxygens in here, but neither of the molecules have an H that's directly connected to an O, an N, or an F. All right, next one, CCl4, so carbon tetrachloride, those are, that is a nonpolar molecule. There are polar bonds, but they cancel each other out, so overall it's a nonpolar molecule. So when we have two nonpolar molecules, the only type of intermolecular force they can have is London dispersion forces. All right, the last one, we have formaldehyde and carbon tetrachloride. So here you might have seen, okay, well, this is polar and this is non-polar. So first you checked off, all right, London dispersion forces, yes. But then when you went to evaluate if there were dipole forces, hopefully you remembered that for dipole forces to occur, both of the molecules have to be polar. And so this molecule overall is not polar. So even though this molecule is polar, since they're not both polar, there cannot be London dispersion. I didn't say that. There cannot be dipole forces. My apologies. I've been recording videos all day. So that is it for a crash course on intermolecular forces. Next up, we're going to go through just a little bit about solubility. I'll see you then.